The second part of this lecture is about abstract machine C. So let's first recall the reduction rule that we developed in the first part, which is kappa expression E reduced to kappa expression E prime if expression E beta reduced to expression E prime. So this is the reduction beta. So the idea was, if you have an expression that is now to reduce to another expression, then this expression can be decomposed into two parts, a red X and the rest of it. And the rest of it is called evaluation context, is kappa. So the problem of reducing an expression now boils down to locating the red X and the rest of it. The rest of it is called this evaluation context kappa. But the problem is, in this reduction rule, the decomposition of the given expression into two parts, this evaluation context kappa and the red X, is implicit. In other words, somebody has told us that the given expression can be decomposed into this evaluation context kappa and expression E, and we don't know how. We were not given specific steps to decompose the given expression into two parts. The decomposition was just given for free. So this may be acceptable to humans, but from the point of view of machines, this implicit decomposition is not acceptable. Everything should be explicit. So here's an example. So let's see the example. This one. The expression E is something applied to expression E prime, and this one is if then else, if then E1 else E2, and this conditional expression is lambda application. So if you are given this expression as a human, you can tell instantly, oh, the beta redox, the red X is found here, and the rest of it is going to be this one. So you can tell instantly the evaluation context is something like this, and the red X is this one. But this is feasible only because you are human. For machine, this is not given for free. The machine is supposed to analyze the given expression by taking several steps, and everything should be explicit. So this is how a machine would analyze the given expression. So first, the machine notices that the expression is something applied to expression E prime, and it has not analyzed the first sub-expression yet. So it is going to rewrite the whole expression as, so in the beginning it starts with something like this one. In the beginning, I'm going to analyze the whole expression. So let's write it as whole filled with this expression. Next, the machine thinks I'm going to analyze this expression, but it is an expression applied to expression E prime. So I want to analyze the first expression to see what it is. So it goes into the first sub-expression. Therefore, the current evaluation context becomes this one, and the machine decided to analyze this expression. So let me make a copy of it here. If lambda x a dot e value v, then e1 else E2. Now the first step in the analysis is explicit. Next, the machine analyzes this expression and then it finds that it is something if blah blah blah, then E1 else E2. And at this moment, it has no idea what kind of expression lies here. So the machine decided to go into this expression and analyze it. So it rewrites the evaluation context this way. The new evaluation context is if E1 else E2 expression E prime. So the structure, the evaluation context obtained from this one goes to the position of this hole, and we obtain this one. And now the machine decided to analyze this expression. Now, analyzing this expression leads to the conclusion that we have reached the red X. So now we have finished decomposing the given expression into two parts. The first part, this evaluation context, and the second part, the red X. So now we are ready to apply beta reduction. So if you jump from this expression directly to this decomposition, it's the way that humans do. But in the case of machines analyzing the given expression, every individual step, every step here should be explicit. And that's the basis for developing this abstract machine C. We'd like to make the analysis, this analysis explicit rather than implicit. So that's the idea. Let's develop this idea further. So in the case of abstract machine, so previously we used this evaluation context kappa, but downside of using evaluation context kappa is the analysis is implicit. Some oracle is going to tell how to decompose the given expression into two parts, this evaluation context and red X. But that's no longer the case once we think about implementing a concrete machine. So the idea is now we ditch this notion of evaluation context, and instead we introduce something called the stack of frames. So we have a stack sigma, and this stack is literally stack of frames. So we have another definition frame for which we use phi. So stack is literally stack of frames. So inductive definition is the bottommost element of the stack is this hole, and you have a sigma extended with this frame phi. So if you feel uncomfortable with this definition, then you can simply expand it. Then stack sigma is literally the bottommost element, the next frame, the next frame. So we have just literally stack of frames. This is a stack of frames where the bottommost element is this hole. So we have a stack of frames, and this frame corresponds to an individual step in the analysis. So in the case of a call by value, we have three components in the definition of a frame. First, whole expression E, and the second is lambda xa dot E whole, and finally we have if whole then E1 else E2. And this frame basically corresponded to an individual step in the analysis of the given expression. Here's an example. If you have a frame, this frame, it means that I'm currently analyzing an expression, but it looks like this expression has some expression applied to expression E. So I'd like to analyze the first sub-expression. In this case, you obtain frame whole expression E. So in other words, if you have a frame whole expression E, it means that you were previously analyzing an expression of this form. And we decided to go into the sub-expression. And if you have a frame of this form, it means that currently you are analyzing some expression, and this expression has this form, and then another expression. And you don't know if this is a value or not, so you decided to further analyze this expression. In that case, you leave a frame of this form. It means that previously I had some expression of this form, and we decided to move on to this sub-expression. And finally, if you have this form of frame, that means that you are currently analyzing an expression, and then you notice that it has this form, some expression, then E1, else E2. So you decided to go into this sub-expression to see what kind of expression it is. So in this case, you leave behind this frame, E1, else E2. That's the intuition behind this frame. So each frame corresponds to one step in the analysis of the given expression when we are searching for the next radix to be reduced. Let's further formalize this idea. So first, we need this operation of filling the hole in a frame, like this one, and then filling the hole in stack. So first, so first we need this operation, frame filled with expression E. So this is easy because it literally says you go to the frame phi and find the hole in it. So this frame, if you look at this definition, every frame is going to have a hole in it. This one, and this one. And also notice that this frame is not inductively defined. It is just three components, and these three components are first component, second component, third component. These components are defined independently of each other, so it's not defined inductively. And this notation just says find the hole in frame phi and then fill it with the expression E. That's all. So for instance, if you have this frame and if you have, let's say, E prime, and literally it is fill the hole with this expression inside the bracket, it's going to be E applied to E prime. That's all. So I'm sure everybody now knows the how this operation works. Now let's generalize it to a sigma with expression E. And if you expand this inductive definition, you obtain this equation. So in this case, sigma bracket expression E is, first, you go to this topmost frame and then fill the hole in it with expression E. So you have this one. And it gives you a slightly bigger expression, this one. a slightly big expression, and you have a phi n minus 1 here. And then you use this expression to fill the hole in the next frame. So now you have phi n minus 1, phi n expression E. And now you have a slightly bigger expression. And then you use this expression to fill the hole in the next frame, and so on, all the way down to this one. So formally, you can write it as if sigma is equal to this stack of frames, then it's going to be phi n with expression E, and this one is used to fill the hole in phi n minus 1, and this one is used to fill the next frame phi n minus 2, and so on, all the way down to phi 1. So the definition looks scary, but it's pretty simple. You just keep filling the hole in the frame one after another, starting from the topmost frame, ending up with the bottommost hole here. So now we have the definition of a frame, definition of a stack or stack of frames, and we also have these two notations. Now let's go back to this example and see how you would rewrite the decomposition in the explicit way using frames. So in other words, let's use frames or stack of frames this time and then rewrite it. So the expression is if lambda x e dot e of double prime value b, then e1 else e2 applied to expression e prime. So we'd like to analyze this expression. First, you start with the bottommost element hole, and so you start with this stack. So this is a stack of frames, the sigma. So this is a special case of stack. So this is the sigma, and you are currently analyzing this expression, and then you find that this expression is some big expression applied to e prime. So what you do is rewrite it as the bottommost element in the stack stays the same, and then you find that the whole expression is something applied to e prime. So you leave something applied to e prime. So you introduce a new frame here. This is a new frame, and then the next expression to analyze, sub-expression to analyze, is this one. So you copy it. If lambda x a dot e double prime value v, then e1 else e2. Now the stack of frames has grown by one element, and the story is the same now. You analyze this expression and then find that it is if something, then e1 else e2, and you don't know what kind of expression it is. As a human, we can tell instantly this expression is this lambda application. But from the viewpoint of a machine, it is unknown what kind of expression this is. The machine is supposed to explicitly analyze this expression for itself. So we keep the previous stack of frames and add a new frame, which is if whole, then e1 else e2. And next, we'd like to analyze lambda expression applied to value v. At this point, the machine realizes that it has reached the red X. So now it's time to apply beta reduction. So perhaps at the next step, this one will be reduced to V4X in expression E prime, and then the machine will further analyze this expression. The machine should analyze this expression again because it may not be a value, and the story goes in the same way as before. So if we rewrite the previous example using stable frames, we would obtain this decomposition, this stack of frames, and this red X. Now let's put together all these observations and ideas to formulate abstract machine C. So here comes abstract machine C. So just like any machine that we find in computer science, this abstract machine C has a state. And it turns out that it has two states. State S is either stack of frames sigma, right triangle expression E, or stack of frames sigma, left triangle value V. As a side note, there's no particular meaning in the choice of the name for this abstract machine, C. So there's no particular meaning in C. So the idea is that if the machine is in this state, we are currently analyzing the structure of expression E because we don't know if expression is red X or if it is a large expression that contains a red X as a sub-expression. We don't know what kind of expression it is. So if the machine is in this state, it is currently analyzing the structure of expression E to see if it is red X or it should be further analyzed. And if the machine is in this state, that means that previously it had this state. And we have done everything we could do with this expression, and we have produced the value V. So in other words, we have finished evaluating this expression E, and the result is value V. Now we are returning this value V back to this stack of frames. So that's the idea. And of course, this machine, abstract machine C, goes through transitions of state. So you start with some state, and then the next state, and then the next state, and so on. So we use this judgment, state transition judgment. This is the machine C transitions from the state S to a new state S prime. So this is a new judgment, and now the remaining job is to figure out the reduction of the inference rules for this state transition judgment or this state transition rule. State transition rules. So let's develop these state transition rules, assuming call by value. Let's assume call by value. And once you have a proper understanding of the meaning of these states, actually, it's fun to develop these state transition rules. So the students are encouraged to develop these state transition rules on their own without looking at the solution in the course notes. It's actually fun, and it's also going to. And this exercise will also help you to complete assignment 6, in which you are going to design a new abstract machine. So let's see how this state transition works. So in the beginning, perhaps you will have something like this one. You start with this state, and in the end, you will have this one. So that's the or generally you can generalize the You can generalize this phenomenon. If you start with the sigma right triangle expression E, perhaps if everything goes okay, then you will end up with this state at some point in the future. Let's develop the reduction rules. First, So let's develop the reduction rules. First, what happens if you have this one, a special case? You are trying to analyze the value, this expression, but you have discovered that it's already the value. So now it's time to reverse the direction and start to return this value back to this frame, stack of frames. So the next state is going to be sigma left triangle value V. That's the first rule. So this rule says I wanted to analyze the structure of this expression, and I haven't discovered that it is a value. So there's no point in further analyzing this expression. So now I return this value V back to the stack of frames. So that's the first rule. What about this rule? Sigma analyze expression E1, E2. I'm currently analyzing this expression E1, E2 because we assume call by value reduction strategy. We have to further analyze this expression E1. We don't know if expression E1 is a lambda abstraction or another application or more complicated expression. We don't know. So we have to analyze this expression E1. So the next state is we add this frame and then keep analyzing expression E1. You needed to leave expression E2 because later when you come back, when you return, you have to restore this expression E2. Now suppose that everything goes okay. From here, everything goes okay. Then perhaps you will generate a lambda expression from expression E1. So later, perhaps you will have something like sigma whole expression E2. This is lambda abstraction. Now you are returning this value V. Then what is the next state? Because we assume call by value reduction strategy, we are not ready to apply beta reduction because we don't know if this expression E2 is ready for beta reduction. It may be a value or it may not be a value. So the machine is supposed to analyze this expression E2 explicitly. So the next step is you want to analyze this expression E2. Then the question is, what is the next frame? We have to remember the fact that we had some expression like this one, because this one is going to fill this hole. So it's as good as having this lambda application. And we are going to analyze expression E2. So the next frame is this one. And then we keep analyzing expression E2 because we don't know if this is value or not. And later, if everything goes okay, this one will return another value V. And this time, we are ready to apply beta reduction. You have lambda, and this one is going to fill the hole here. So you have lambda applied to value V. So in the next step, we will have expression V for X in expression E. And the question is, should we use a right triangle or left triangle? And the answer is, we have to use a right triangle because we don't know if this is a value or not. Perhaps this is not a value because expression E is not value. So we have to analyze this one. So the direction of a triangle is right. You have to use the right triangle. And the remaining inference rules are straightforward. So for example, sigma, if expression E, then E1, else E2. You have to analyze the expression E. So you add this frame to the stack, and then you keep analyzing expression E. And if everything goes all right, then expression E is going to evaluate either true or false. If this expression E produces true, later we will have something like if, then E1, else E2. Later we will return value true. And then what is the next state? We are going to take the expression E1, so it's going to be sigma, and then we have to do something about the expression E1. And of course, we want to keep analyzing expression E1, because in general, expression E1 is not necessarily a value. So you have to check if expression E1, again, if expression E1 happens to be a value, at the next step, we will apply this state transition rule, and then at the next step, we will return expression E1 if this is a value at all. And similarly, there is the symmetric case of false.